All right, yo, what's up, guys? So today we're going to be talking about position in one dimension, and we're going to be talking about the calculus connection. So we, in the last video, were mentioning the concept of position and the graphs and etc. But today we're going to be talking about the calculus connection. So as you can see over here, position is the base function for motion and all foundations of kinematics. All other motion quantities are derived from it using calculus like velocity and acceleration. So as you can see over here, we can find that by differentiating the positions. And we know that velocity is the first derivative of position and acceleration is the second derivative of positions. And these are the derivative formulas for both velocity of time and acceleration of time. And if we're conversely knowing a v of t or a of t, you can integrate it to find x of t, which is the position function. So as you can see, this is the formula, the integral formula. So differentiating positions usually equates to motion rates, and integrating motion rates usually equates to position. All right, yo, guys, so basically we're now going to be talking about the key rules to remember. So as we mentioned before, you always have to start from position x of t. And we know that for the first derivative, you have the derivative of position of x of t, which it then gets you velocity. And then for the second derivative from velocity, you then get acceleration, which would get you a of t. So if we're focusing on derivative-based motion, you'll always go forward. So the way the key chain works is you go from position to velocity to acceleration. So that's why every motion problem we follow using this chain goes from x of t, which you then differentiate to get velocity of t, v of t, and then you get a of t. So if you ever go backwards though, as we mentioned from the problem before, using the integral formulas, you get a of t to then v of t to then x of t. So then you therefore integrate and you don't differentiate.